Hi everyone, let's go ahead and uh, give some explanations of these reactions. Okay, question number 20, what is the major product of the following reaction? So we have an epoxide here with a methyl group attached to it, and then we are going to do this reaction in the presence of an acid, HBr. So what is going to happen first is the lone pair of the oxygen of the epoxide is going to protonate, okay, with hydrogen bromide. So you will get a protonated epoxide. Oxygen first will get protonated and you will have a protonated epoxide. This happens only in the acidic medium. If it is a basic medium, oxygen will not get protons. Okay, so the next step is the bromide is going to attach either to the carbon on the left or the carbon on the right. So when this happens, the bromide tends to go to the one that is more substituted, because that is the carbon where we will see most stable carbocation. Okay, okay, so if it goes to the left side or the epoxide opens from the left side, you will create a primary carbocation. And if the epoxide opens from the right side where the carbon number 2, you will get a secondary carbocation. So which one is most stable? It's a secondary carbocation. So always keep in mind, if an epoxide is going to open in the acidic medium, you will first protonate the oxygen and you choose the carbon that is most substituted. In this case is going to be number 2 carbon, and that is where the incoming nucleophile, in this case it's bromide, is going to attack. Okay, because that's where the most substituted or most stable carbocation, which is secondary over primary carbocation. So as a result you will get this final product, OH group on the first carbon, and on the second carbon you have the substituent methyl group as well as the bromide attached to that. So the second question also similar to that. Again we have epoxide in the medium, acidic medium. First step would be protonating the oxygen, right? You will have a protonated epoxide, and then the next step is incoming nucleophile. This case is going to be methanol molecule, CH3OH. So I'm drawing here the protonated epoxide, and now you know there are two sides, left carbon or the right carbon, that it can attack. Now the second carbon or the right carbon would have the most substituted carbocation, so the methanol CH3OH will go to the B carbon. The choices side can go either to A or B. A would create a primary carbocation, B would create a secondary carbocation once the oxygen carbon bond breaks. So methanol lone pair of the oxygen will go to the carbon B and open up the epoxide. So this is going to be your protonated epoxide. Now it has only one lone pair. Incoming methanol molecule will go to the carbon B, because once the OH bond breaks, oxygen carbon bond breaks, you have a tertiary carbocation there. That's the carbon number 2. Okay, so you will see carbon number 1 has the OH in it and also the CH2, two hydrogens on that carbon. And then the carbon number 2 has its original 2 methyl groups, and then the methanol group, incoming group. Now it will still be protonated with the hydrogen on the oxygen, and another methanol molecule will come and grab that excess hydrogen from the oxygen, giving you the final product. So by looking at the product, you can choose the correct answer. That's going to be the final product. Again, this is the epoxide opening under acidic medium. Now this question tells us what to do when you are trying to open an epoxide in the basic medium, methanol and methoxide. Do we see any protons or the acids here? No, it's a base, methoxide, comes from the sodium methoxide. So we are not going to protonate our oxygen because there are no protons. So the methoxide will directly attack one of the carbons of the epoxide. So when the methoxide attacks, it's always going to choose the most available carbon or the least hindered carbon. If you look at the left carbon next to the oxygen or the right carbon next to the oxygen, where you have 2 methyl groups, which one is more hindered? The carbon with the 2 methyl groups, which is carbon B, is more hindered. So when the methoxide anion comes, it would choose the one that is more open carbon. So then which one it is going to attack? It would be the carbon A. So no carbocation formation in this case. So methoxide attack the carbon A, carbon oxygen bond breaks, and you will form oxide anion. Methanol CH3O group will be attached to carbon A. Carbon A already has 2 hydrogens on it, so you have to draw that 2 hydrogens. Then you go to the carbon B, it has 2 methyl groups and also the oxygen anion, O minus. Now the final product. So this is a 2-step reaction. First step you add the methoxide, and in the second step you are adding methanol. So methanol hydrogen would serve as a proton source for the oxide ion to be protonated. Okay, so you grab that hydrogen from the methanol and complete the process of making the alcohol. So in the presence of a basic medium, you always remember that the anion attack directly to the carbon which is least hindered or more open carbon. And then you follow which atoms or groups are attached to each carbon. Now, question number 23. Draw the major product of the following reaction. We have an alkene. We are going to react this with the CH3CO3H. This is not a normal acid. Normal acid are CH3CO2H. Here you can see there are 3 oxygens, which is a peroxy acid. Excuse me. Which is a peroxy acid. This is a normal acid, CH3COOH, carboxylic acid. Formula would be CH3CO2H. So the peroxy acid, the structure is given here. It has 2 oxygens next to the carbonyl group. Peroxy acids are used to make an epoxide from alkene. There are 2 steps. So the first step is peroxy acid making an epoxide with the alkene. In your second step, you have a NaOCH3 methanol. That is the conditions we normally use to open an epoxide in the basic medium. Sodium methoxide you have sodium ion, sodium positive ion, and methoxide anion. And then the second step, adding methanol. So similar to our previous example of opening an epoxide in the basic medium, same thing happens here. Methoxide is going to be your incoming nucleophile. It can either go to A or B. A is more hindered, B is more readily available, it is more open. So methoxide ion will now attack A or B. It's going to be B because it's more open. There are no protonation. So it would carry OH group on the carbon A, and on the carbon B you will have the methoxy group attached. That's going to be the first step, having oxide anion, and then the second step it would protonate with methanol. So I have drawn here the final product since I explained the complete steps in the previous example. Okay. So the final product is this. So it's a two-step. First would be with the peroxy acid, it would form the alkene. Alkene would form the epoxide, then opening in the presence of a base, methoxide. The next question is similar, where you're going to do the same thing now with the acidic medium. Again, similar to the previous one, alkene would form a epoxide in the presence of peroxy acid, and then we have methanol in the presence of hydrogen ions. Now the epoxide ion opening in the presence of a acid catalyst. First would get protonated, so then the methanol will add to the most substituted carbon, which is the ring carbon. And number 25, what alkene is formed in greatest yield in the following Hofmann elimination. So the Hofmann elimination, you have a quaternary ammonium salt. Quaternary means nitrogen has 4 alkyl groups on it. For Hofmann elimination to take place, we need to have a beta hydrogens on the beta carbon. Carbon next to the nitrogen is the alpha carbon, and then the further to the left would be beta carbon. Okay, so CH3, CH2, CH2, and then we have the nitrogen with 3 methyl groups. Nitrogen with the carbon carrying the 3 methyl groups. And then the base would come and grab a hydrogen from the beta carbon of the molecule. And then the carbon hydrogen bond breaks and gives its electron to form a double bond with those 2 carbons. And nitrogen, since nitrogen is already positively charged, it can leave as a neutral molecule, generating an alkene plus the tertiary amine and a water molecule. That is the Hofmann elimination, forming alkene and then the ammonium product and water. How many signals would you expect to see in the proton NMR spectrum of the following compound? Excuse me. So this molecule, if you expand it, is CH3, CH2, CH2, CH3. So this is a symmetrical molecule, meaning if you divide the molecule to half, you will have 2 exact halves, right? So CH3, the 2 CH3 groups on the either side, they are in the same chemical environment, and then the 2 CH2s will be experiencing same chemical environment. So we have 2 signals because 2 methyl groups will give us 1 signal, 2 methylene groups, CH2 groups will give us another signal. So there are going to be 2. So 27, if you look at, there are 4 different signals. Why 4? Because there are 4 different environments that hydrogen are on 4 different carbons. Okay. So you see here on 27, CH3, the first CH3 would be one environment, and then the CH2 would be another environment, and then the third carbon having a hydrogen and chlorine, that's a different carbon environment. The last one, methyl group, is another one. So as a result, there are going to be 4 different chemical environment, and as a result we will see 4 different proton NMR signals. They are not equivalent because the molecule is not symmetrical. Okay. So the next one, 28, which of the following methyl groups gives NMR signal with the highest frequency? Meaning which one gives us the signal most downfield or higher frequency. So we are looking at the methyl signal. So you have to see which methyl group is more closest to the most electronegative atom. Okay. So the first one is methyl next to a NH2 group, nitrogen. And then the second one, methyl next to a oxygen. Okay. So basically, if you have a methyl group next to a nitrogen, it could be, the chemical shift would be somewhere around 1.5 to 4. 1.5 to 4. If a methyl group next to an oxygen, it would be somewhere closer to 3.3. Between nitrogen and oxygen, which one is more electronegative? Oxygen is more electronegative. And you can also have a methyl group next to a carbonyl group. So methyl group next to a carbonyl group comes somewhere around 2.1. And then this is an alkane, CH3CH2. So just next to another carbon, that's around less than 1.85. Okay, so that one. And then the last one, methyl group next to a benzene ring, that would come somewhere around 2.3. So next to the oxygen is 3.3. So that would be the most downfield or higher resonance would be next to the oxygen. And all the numbers you can see from your slides. I think it's slide number 25 on your NMR lecture. Slide number 25. You can see the approximate values of chemical shifts. Okay, so you can see that. But in this case, all the elements next to the methyl group was either carbon or nitrogen or oxygen. So the oxygen being the most electronegative atom, you can assume that methyl would come more de-shielded or higher frequency. Okay, that was for question number 28. And then the next one, what is the ratio of the protons in the following compound? Now this one, the 2 methyl groups are in one environment, 2 hydrogens on the CH2 are on another environment. So the ratio is 6 to 2. If you make it smaller, that would be 3 to 1. Okay. There are 2 different chemical environment giving us the ratio 3 to 1. And what splitting pattern observed in the proton NMR spectrum for the indicated hydrogen? Indicated hydrogen is at methyl group. Remember, always you will have a splitting due to a 3-bond coupling. Meaning you need to have a hydrogen on the neighboring carbon atom. But in this molecule you have a methyl group CH3 and next to it is oxygen. So through oxygen there are no coupling takes place. So as a result, that the 3 hydrogens in that methyl group will give you a singlet, since it's not going to split by any other hydrogens. Okay. Number 31, give the splitting pattern for each set of protons in the proton NMR spectrum. So if you look at your carbon A, it will be splitted by the hydrogens on the carbon B according to the n+1 rule. Right? What is n is the number of hydrogens. So for the methyl group A, it will be splitted by the 2 hydrogens on carbon B. So 2 plus 1 would be 3. So the A hydrogens would be therefore a triplet, n+1 rule. If you look at CH3, that's going to be a triplet because it's going to split by the hydrogens on the carbon B to a triplet. And then the B, carbon B, would be splitted according to n+1 rule. 3 plus 1 would be a quartet, 4. And C, carbon C, will be splitted by 2 hydrogens on D, giving us a triplet. And then the D, there are 2 hydrogens on carbon D. That can be splitted by hydrogens on carbon C and carbon E. So there are 2 on carbon C, 3 on carbon E, 5. But they are not going to be equivalent because their connections are different. So as a result, we will see it as a multiplet D. And E would be a triplet because there are 3 hydrogens on the carbon E. It would split by the 2 hydrogens on the carbon D. Since it's 2, 2 plus 1 would be a triplet. E would be a triplet. Okay. Okay. Number 32. Identify the compound with molecular formula C4H8Br2 that gives the following proton NMR data. We are given 2 sets of information. Singlet at 1.97 ppm, 6 hydrogen singlet. And then another singlet at 3.89 ppm. If it is 6 hydrogen singlet, we can assume that there are 3 hydrogens. 2 sets of 3 hydrogens, singlet. And on this carbon, the middle carbon should not have any hydrogens in it. If it does have a hydrogen, that 6 hydrogen has to be a doublet. But since it's a signal, that carbon cannot have any hydrogens on it. Okay, so we found one piece of information. And then we are also given another singlet, 2 hydrogens, meaning you have 2 hydrogens on the carbon and the neighboring carbon should not contain any hydrogens, because if it does, then it cannot be a singlet. And look at the chemical shift, 1.97 and 3.89. 3.89 meaning it's downfield compared to 1.97. So that 2 hydrogen should be directly connected to a bromine. And 1.97 also more downfield compared to if you don't have a electronegative atom. So now we found the 2 pieces. We can combine them together, giving us this molecule. 6 hydrogen singlet, 2 hydrogen singlet, and their chemical shift also resembles the connectivity directly to electronegative elements. Okay, that is the molecule.